Hey everyone, welcome back to another video. In this video, I'm going to be going over lines and linear relationships, and this is the first video of the video series on functions and graphs, trigonometric functions, and exponential functions. So this is the second topic and unit 1 of the second topic. I should mention that this topic, functions and graphs, trigonometric functions, and exponential functions, will be quite long, given that it's grouping 3 different subheadings from the SCASA syllabus. But this video will be relatively short because it goes over a lot of the content that you've already had a look at in previous years. Something I should mention is that the order I'll be going through this topic might not match up with the way your school teaches it. You might have a look at trigonometric functions earlier before you actually look at functions and graphs or lines and linear relationships, for example. So I leave it at your discretion to decide the order you watch this video in. But I'll go over an introduction of our unit. So the unit overview, we're going to be going over lines and linear relationships. We're going to be having a look at the features of a Cartesian plane when a line is plotted on a Cartesian plane, that is y equals mx plus c. And we're going to have a look at the important points associated with that. So where does it intersect the x-axis? Where does it intersect the y-axis? What is its gradient? Okay. After we've had a look at that, we'll be looking at the relationship between the equation of a line and its graphical representation. We'll be able to figure out how to determine the equation of a line given a graph of a line, and vice versa. So we'll be able to graph a line on a Cartesian plane given an equation as well. So let's get straight into it, and I'll turn my camera off.
Okay, so the first thing I want to draw attention to is the equation of the line y equals mx plus c. This equation has two distinct features. First, it has a gradient, which is denoted by the letter m, and second, it has a y-intercept denoted by the letter c. If we look at the graph of this line on a Cartesian axis, which is an xy plane, so this is my y-axis, this is my x-axis, my line will look something like this. Okay? And it will have an associated y-intercept of c, and it will have a gradient m. When I talk about the gradient, okay, what I mean is the slope of the line. What do I mean by slope of the line? By slope of the line, I mean how much y increases by, for every 1 unit increase of x. And so the way I represent that is what I'm doing right now. Okay. And my gradient that I've drawn up here is equal to the rise divided by the run. Here, the rise is this vertical point here, and the run is this bit here. And so dividing by my rise by my run, I get how much my y increases for every 1 unit increase of x. This triangle is marked out by 2 distinct points on the line. Okay, I'll denote this point here as x1, y1, and I'll denote this point here as x2, y2. So these are arbitrary denotations for those points, but we'll see that it's really important to give them these denotations when I write a different formula for the gradient. The rise here can be written as the difference of 2 coordinates. More specifically, it can be written in this case as the difference of y1 and y2. The rise is the difference in the y coordinates. Rise equals y1 take y2. The run, I'll do that in a different color maybe. The run is given as the difference between the x coordinates. The run is equal to x1 minus x2. So, if the gradient is given by rise over run, then it's also given by y1 take y2 over x1 take x2. The important features here are that this y1 is on the left-hand side of the difference, and this y2 is on the right-hand side, and similarly this x1 is on the left-hand side, and the x2 is on the right-hand side. So these are the set of coordinates of the second point, these are the set of coordinates of the first point. We can also equally write this as y2 take y1 over x2 take x1. The only important thing is that we match up the coordinates in this way. Okay. So if, in this case, we can see that the gradient will have a positive value. And the reason why that's the case is because we can see that y is increasing for a 1 unit increase of x. Y increases for an increase in x. So my y1 is greater than my y2 for x1 is greater than x2. Okay. And this indicates that we have a positive gradient or a slope. If, on the other hand, we have a decrease in y, so y decreases for an increase in x, this would imply that we have a negative gradient, or slope, and it would be given, the line would be given by something, would look like something like this. Okay, so this is a negative gradient, and this is a positive gradient. Okay, so we've had a look at gradient now. Let's have a look a bit more at the y-intercept. So if we've got an associated gradient, we know that it'll have a gradient like this. And if we have a c, then for every 1 increase value in x, it'll have an associated m increase in y. What the y-intercept does is it shifts the line up from initially being through the origin, which is this point 0, 0, and it shifts it c units up in this direction. So that's called a translation of c units upwards. And so if y equals mx passes through the origin, y equals mx plus c passes through the point 0, c. All right. We also know that a line looks like this. We've looked at the linear nature, so that's a tick. We've looked at the slope or gradient, which is a tick. The intercepts, we've also got the c here. We can also note that we've got an x-intercept here, which we can denote by d, but that's not as important. It is important if you are graphing a line that you indicate all of the intercepts. So if you're given a graph this line question, you'll need to make sure you get the gradient right, first of all. You'll need to make sure you get the y-intercept right, and you need to make sure you pass it through the correct x-intercept as well. These will all be features of a line, unless you've got a horizontal or vertical line. If you've got a horizontal line like this, then it won't have an x-intercept, and if you have a vertical line like this, it will have no y-intercept. So horizontal lines look kind of like y equals 3, for example. This would be a horizontal line passing through y equals 3, 0, 3. X equals 2 would be a vertical line passing through 2, 0 with no y-intercept. Importantly, this has an undefined gradient, and a horizontal line has a 0 gradient because for any 1 unit increase in x, there is a 0 unit increase in y. All right. Cool. We've had a look at all of that. Now let's move on to the second point. Determining the equation of a straight line given sufficient information, including for parallel and perpendicular lines. Okay, so in this case here, what we're trying to do, I'll expand on this a little bit. Determining the equation of a straight line, we have to go from the equation to the graph, and we also need to go from the graph to the equation. So this is kind of a double-sided arrow. These are the two skills that we need to develop through this module. Okay, so let's say we have a line y equals 2x plus 3. What we know about this equation is that it has a gradient 2 and it has a y-intercept 3. So it's going to pass through the point 0, 3. And for each x, 1 unit x increase, we're going to have a y increase of 2. So we know that we pass through 0, 3. If we want to figure out another point in the line y equals 2x plus 3, we can just substitute any value for x into this equation here. So we could sub in x equals 1, in which case we would get y equals 2 times 1 plus 3, or 5. So we pass through the point 0, 3 and 1, 5. And we'll notice here, as we increase by an x unit of 1, we increase by an y unit of 2. Okay? This is all we need to graph the line y equals 2x plus 3. To graph any line, we only need 2 points, because through any 2 points, there is a unique line that passes through them. So if I graph this on a set of axes, so I have my x-axis here, and I have my y-axis like this. Okay, look like this, y and x. I will have a y-intercept of 3 here, and I will have a gradient of 2. So I know I pass through this point, and I know also that I pass through this point here. If I want to figure out what my x-intercept is, I have to set y to 0. And in this case, if I set y to 0, I get 0 equals 2x plus 3. And solving for x, I can get x equals negative 3 divided by 2, which is negative 1.5. These axes might not be perfect, but I've got my 2 points here. I can draw my line like this, and yeah, see, I haven't drawn my axes perfectly, or the units perfectly, so it won't exactly pass through negative 1/2. But if you draw your line properly, it should pass through negative 1/2. So, oh boy, maybe I'll just erase this. All right, draw that again. And so this is the point negative 3 on 2. Okay, so here I've indicated my y-intercept, that's 1 mark. I have indicated my x-intercept, that's another mark. I have shown that it's a line, that's another mark. And I've got a gradient of 2, which is 1 more mark. So the maximum number of marks you can get for graphing a line here is 4. Okay. So let's say I am trying to go from the graph to the equation, and I'll rub all this out so I didn't know any of this stuff. All right, so based on this equation, I can see that I pass through the point 0, 3. All right, so if I have my y equals mx plus c, I know that because I have a y-intercept of 3, my c value is equal to 3. All right, m. If I go here, my m can be calculated by the rise divided by the run, which is equal to the coordinate of the y-coordinate of one coordinate minus the y-coordinate of the other, divided by the difference of the x-coordinates. I've identified one point here, 1, 5, and the other point is my y-intercept, 0, 3. So my gradient will be given by 5 minus 3 divided by 1 minus 0, or 2. And so now I've calculated my m. So y equals 2x plus 3 is my equation. Okay, cool. I'll briefly touch on parallel and perpendicular lines before I move into simultaneous equation solving, which isn't actually given on the syllabus, but it's a necessary part as well. So I move that over and I look at parallel and perpendicular lines. So parallel lines are characterized by the fact that their gradients are the same. So if we have a line 1, which we label y equals 2x plus 3, and then we have a line 2, where y equals 2x plus 1, then these will be two parallel lines with different y-intercepts. This one will have a y-intercept of 3, and this one will have a y-intercept of 1. So if we graph this on a set of axes, and I'm doing this very roughly, it looks something like this. And they would be parallel lines. This one passing through 1, so this is line 2, and this one passing through 3, so this is line 1, line 2. Importantly, one of the characteristics of these lines is that they never actually intersect with each other. And the gradients are the same. So m1 is equal to m2. When it comes to perpendicular lines, what perpendicular lines are lines that intersect at right angles. So if I have a set of axes, this point here will be a 90-degree angle. One example of perpendicular lines are my line again, y equals 2x plus 3. Okay, and the line 2, a perpendicular line to y equals 2x plus 3 is y equals negative 1/2 x plus 7. So the characteristic of perpendicular lines is that the gradient of my one line multiplied by the gradient of my second line will be equal to -1. And here I can see that's the case. 2 times negative 1/2 equals -1. So these are parallel and perpendicular lines. All right, let's say we want to calculate the point of intersection of these perpendicular lines. And I'll just use this as an example, but you can actually apply this to any set of lines, given that they aren't parallel, because if you have parallel lines, they won't intersect at any point. So let's say I'm trying to solve the point where y equals 2x plus 3 and y equals negative 1/2 x plus 7 intersect. The way I do that is through something called simultaneous equation solving. And I'll write that out here. Okay, I have my first equation, y equals 2x plus 3, and I have my second equation, y equals negative 1/2 x plus 7. Now let's say, oh, that should be a 2 there properly. Y equals 2x plus 3. Okay, now let's say I want to solve where these two lines intersect. The point where these lines intersect is where the y values and the x values are the same. So the y values are the same, so that means I can equate negative 1/2 x plus 7 to 2x plus 3, because these y values are the same. So negative 1/2 x plus 7 is equal to 2x plus 3. And so rearranging with algebra, I get 4 equals negative 5. Oh, sorry, not negative 5. 4 equals 5 on 2 x, and so x equals 8 on 5, or 1.6. If I plug that into my equation, so sub into equation 1, then y equals 2 times 1.6 plus 3 equals 3.2 plus 3 equals 6.2. So my point of intersection is the point 1.6, 6.2, or I can also represent this in fractional form as 8 on 5, 31 on 5. Okay? So this process of solving is known as the substitution approach to solving simultaneous equations. That's one approach, and the other approach is known as elimination, which I'll show you now. So we've gone over substitution. I hope this all makes sense. If it doesn't, make sure you ask me in the comments section, but I'm going to move on to elimination. All right. So back to here. Solving by elimination, this, I will admit, is a process I haven't actually grasped conceptually, but I know that the process itself works. And I wouldn't get too caught up with trying to understand how it works conceptually either. But the way that you do it is you eliminate one of the variables y or x by adding some multiple of one equation to some multiple of the other equation, or subtracting some multiple of one equation away from some multiple of the other equation. In this case, it's relatively easy, given that my y's are in a ratio of 1 to 1. So to eliminate my y's, I can simply subtract equation 1 minus 2. So 1 minus 2 gives me y minus y on the left-hand side as 0. 2 minus minus 1/2 gives me 5 on 2x. Minus 4, 3 minus 7, okay? And now I've eliminated my value for y, and I can solve for x. So 5 on 2x equals 4, which implies that x equals 8 on 5. Okay? And now substituting that into my equation 1, I get y equals 2 times 8 on 5, and I'll leave it in fraction form in this case, just to shake things up compared to the substitution approach. 2 times 8 on 5 is 16 on 5, plus 15 on 5 gives me 31 on 5. And so my point of intersection, just like before, and you'd expect it to be the same given we're solving the same set of equations, will be 31 on 5. 8 on 5, comma, 31 on 5. Okay, so this is the coordinates of where these two lines intersect with each other. And that is lines and linear relationships done. So we had a look, let's get my green pen out. We've had a look at the graph of y equals mx plus c. We've seen that it marks out a line. We've seen that it will have an associated x and y intercept unless it is a horizontal or vertical line. And we defined what a gradient was. We saw that the gradient of a horizontal line was 0 because for any 1 unit increase of x, there's a 0 unit increase in y. And for vertical lines, a gradient is undefined. We then had a look at the equation of a straight line and saw how we were able to determine the equation of a straight line given a graph and vice versa. We then also defined the characteristics of parallel and perpendicular lines. So that's 1.2.2 done. 1.2.1. Cool. So that is everything when it comes to lines. It did actually go for quite a bit longer, but I think it's a relatively easy concept. So hopefully not too much new stuff to learn here. Okay, so thank you for watching. Just some reminders. Remember to comment if you have any questions or if I've missed anything. This, as I've mentioned before, is intended to be an interactive platform for you to ask any questions you have. While it would be great if you only comment under the video, comment a question for a specific concept I discuss in a video, if you have any other questions as well, feel free to put those in any comment section and I'll try to get around to those. And make sure you subscribe to ensure you don't miss any new videos. I am posting quite regularly at the moment. You should be expecting videos from me on Tuesdays, Thursdays, and Saturdays. And that way I'll hopefully be done with the entire year 11 and 12 curriculum for specialist chemistry and methods for year 11 and 12 by around July next year. The next video releases on the 12th of October, which is the upcoming, not the 12th of October. Yes, the 12th of October. The next video releases on the 12th of October 2024, so make sure you're subscribed so you don't miss when that video drops. Okay, thank you for watching and I'll see you in the next one.